So what else are humans doing? So we have been responsible for cooling our stratosphere. As I mentioned last time, the depletion of the ozone layer, as well as increased greenhouse gases, have caused our stratosphere to cool pretty significantly. It's eaten up at our ozone layer. And so that has had pretty big impacts on our stratosphere. But what else have we done? Well, I'm sure you've heard about these things called aerosols before. Usually what comes to mind when you hear that term is aerosol cans. That stuff actually smells pretty good, so I don't mind spraying it. Aerosol cans. But what actually are aerosols? Why do we even call those aerosols? Well, an aerosol is any kind of microscopic particle, either solid or liquid, that ranges in size from 0.1 to 10 micrometers. Now, if you remember, a micrometer is really, 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 really tiny. 1/1,000,000th of a meter. So if I took a meter and split it up into a million individual pieces, each one of those of equal size, each one of those would be a micrometer. So these things are really, really, really tiny. And there's a few that you may have heard of before. PM 2.5 and PM 10. Those are two different types of aerosols. 2.5 are aerosols that have a diameter of 2.5 micrometers. And then 10 are ones that have a diameter of 10 micrometers. So aerosols are these tiny little particles that are either solid or liquid suspended in our atmosphere. Because they're really, really tiny, there's actually a lot of drag and a lot of resistance as they fall, and that keeps them kind of floating in our air. The upward force that they feel from drag counteracts the gravity that they feel pushing down on them. So that being said, these aerosols can act as this thing called a cloud condensation nuclei. And I'll tell you what that means in a few minutes. But they can also alter Earth's radiation through these two effects, the direct effect and the indirect effect. So the direct effect and the indirect effect. And we'll talk about each one of those right now in this video. Okay, so with that being said, let's talk a little bit about aerosols. So aerosols don't hang out for long in the atmosphere. When an aerosol gets up in the atmosphere, through one process or another, it will eventually float its way back down to the surface. So these don't hang out for long in our atmosphere. They can be there for a few days to maybe a couple of weeks. That's about it. And during that time, new aerosols are getting kicked up, and then those come down, and the new ones get kicked up. Once they get into the stratosphere, however, the weather in the stratosphere is very, very, very boring. I mean, think of this class and make it way more boring than that. That's saying something. So they're really, really, really boring. The weather in the stratosphere is really, really, really boring. As a result, these aerosols, once they get into the stratosphere, they can hang out there for years. So in the troposphere, because of wind, because of mixing that happens, they eventually make their way back down to the surface. In the stratosphere, because the weather's so boring, they can kind of hang out for a really long period of time. And then they either return to the ground, or they go into the ocean, or they settle their way back down here to the surface of the Earth. So what are some examples of aerosols, these little microscopic particles? Well, there are actually a lot of natural examples. Dust, for example, is a type of aerosol. Smoke. If you ever see a wildfire, even if it's a naturally caused wildfire, there's smoke coming out of it. Well, that smoke is made up of trillions and trillions and trillions of these little aerosols, including things such as sulfates, black carbon, that's this dark elemental carbon. It's almost like a tiny little chunk of coal. Organic carbon, salt. if you ever go towards the ocean and you see waves crashing and you kind of smell that salty smell, what's happening is when the waves are crashing, they're kicking up salt into the atmosphere, and even bacteria. So there are even bacteria that are present in our atmosphere as aerosols. What's actually really crazy, before I get to that picture, what's actually really crazy is even in very, very clean air. I'm talking air that's cleaner than anything we've ever breathed. Very, very clean air. There may be 10,000 aerosols per every cubic centimeter. It's about the size of your pinky tip. 10,000 aerosols per every cubic centimeter. So that just goes to show that there are a lot of aerosols in our atmosphere. There are a ton of aerosols in our atmosphere. Now we can actually see aerosols. We can't see individual little aerosols because they're so tiny, but when you get a bunch of them together, you end up getting a haze that forms. Let me show you what I mean. So this is a day where there is a low amount of aerosols in the atmosphere. This is Denver, Colorado, amazing city. If you've never gone, you need to go. It is an awesome, awesome, awesome city. And this is Denver, Colorado on a day with a low aerosol content in the atmosphere. So here you are east of Denver, Colorado. You can see the Rocky Mountains all the way in the back. Here's downtown Denver. Look at this brown building right here just for reference. So this is Denver, Colorado on a day where there's not a lot of aerosols in the atmosphere. This is considered a good air quality day. This is the day where the air feels nice and fresh. The air quality is really good. Well, now let's take a look at a day when there's a high aerosol content in the atmosphere. This is Denver, Colorado, same city. Notice that brown building down there. Same city, but now we have a day with very poor air quality. On this day, there's a lot of soot in the atmosphere. There's a lot of ozone in the atmosphere. There's a lot of little particulate aerosols, things such as black carbon, smoke that comes out of the tailpipes of cars, sulfate aerosols that come from burning of coal. And if you notice, on this particular day, the air quality is really, really, really bad. And whereas you had this beautiful, clear view of downtown Denver here you don't get that. And kind of pick out, if you actually zoom in, you can kind of pick out a few skyscrapers. But really, downtown Denver here is gone. Can't see it. Because the air is so thick, there's so many aerosols in the air that they prevent you from seeing it. They actually change the optics of the atmosphere to the point where you can't actually see them, where you can't actually see much further. So that's a bad air quality day. Now, what causes bad air quality days? Believe it or not, the number one answer has to do with the weather. On days where the air is very stagnant, meaning there's very little wind, usually there's this big area of warm air higher up and cold air near the ground. That's what's called an inversion. You'll usually see something like that that'll trap, it basically behaves like a lid, trapping all this dirty stuff down near the ground. That's a little beyond the scope of this class, but I just wanted to mention that. So this is a day where there's a lot of aerosols. So these aerosols are pollution. And we usually see pollution as large clusters of these aerosols. Now, what actually happened in the 50s and 60s, we had an incident, or we had a number of incidents where the air quality got so bad, it actually started causing breathing problems. It actually started killing people. There were actually smog crises in the United States and in England, one in particular called the London smog that killed about 5,000 people. So pretty big thing. There was a smog crisis in a small town in Pennsylvania called Denora during this time, and it caused a lot of death. It caused a lot of problems. And as a result, in the 50s and 60s, most developed nations began developing clean air laws, anti-pollution laws to sort of clean up our act. Unfortunately, greenhouse gases were not a part of those Clean Air Acts. We were more worried about things like elemental carbon, organic carbon, soot, smoke, and so on. And so we created emission standards to reduce those, but we really didn't focus on greenhouse gases at the time, which is why, unfortunately, greenhouse gases have continued to increase in concentration. Okay, so what do these aerosols actually do to our planet? What do they do to our heat? Well, there are actually two types of effects that aerosols have on Earth's heat budget. There's the direct effect and the indirect effect. And so I'm going to talk about each one of those very briefly right now. The aerosol direct effect is the effect that the aerosols themselves have on incoming radiation and outgoing radiation. So if I have a little aerosol right here, let's say this is an aerosol, and I have a beam of incoming shortwave radiation, the aerosol can actually reflect that. It can also absorb it. So incoming radiation now being absorbed by the aerosol. The other thing that it can also do is, if you remember, not only are aerosols giving off, or sorry, not only is the Earth receiving radiation from the sun, but the Earth is also giving off radiation, what is called long wave radiation. Well, those aerosols can actually absorb that long wave radiation as well. So what I really want you to know here is that the aerosol direct effect is the effect that the aerosols themselves have on Earth's surface energy balance. They can reflect shortwave radiation, preventing it from reaching the surface of the Earth. They can absorb outgoing long wave radiation. They can absorb incoming shortwave radiation. Any one of those three things affects Earth's energy budget, either what's coming in or what's going out. And therefore, any one of those three things can affect Earth's temperature. In general, when adding these things up, it is believed that the net effect of the direct effect is cooling. The reason why is because two of these three processes, two of these three effects, two of these three direct actually prevent sunlight from reaching the surface of the Earth. Therefore, the Earth doesn't absorb as much sunlight. Therefore, the Earth cools down. Therefore, the Earth cools down. So the net effect is believed to be cooling. So once again, the effects that that aerosols can have include things such as reflection, and absorption of incoming radiation, as well as absorption of outgoing radiation. Those are the direct effects. And we can actually see this on a daily basis. When you actually see aerosols, when you see those pollutants, when you see that stuff coming out of the tailpipe of a car, or coming out of the smokestack of a truck, or coming out of the chimney of a factory, what you are actually seeing right at that moment is the aerosol direct effect. You are seeing all those little aerosols actually affecting incoming sunlight. So you're actually seeing that. And as a result, we've actually seen an increased concentration of aerosols. As human activity has gone up, as more people have driven cars, as more factories have been built, we have seen an increase in aerosols. Now, what about the indirect effect? Well, the indirect effect is actually a secondary set of effects that aerosols have in the atmosphere. Here's basically what they do. Aerosols actually act as these little things called cloud condensation nuclei. Here's how it works. Did you know that at the center of every cloud droplet, so if you look outside, you find a cloud, you look at that cloud, believe it or not, every single droplet has a little aerosol particle in the center of it. In order for water to condense, it needs some kind of solid particle, some kind of non-water particle for the water to stick to. So let me draw these little H2Os here. And they, boom, stick to the water molecule, or sorry, they stick to this non-water molecule. They stick to this aerosol molecule, causing the droplet to grow. Well, here's the thing though. The more aerosols we have, the more droplets we're gonna have. However, we now have the same amount of water, but it's spread out over a larger number of droplets. That would be like if I had, let's say, a single pizza and 2 people in the room with me. The 3 of us would each get a bunch of pizza. We have 1 pizza to split amongst the 3 of us. Now let's say I had this class, 40, 50 students, 1 pizza now split amongst 40, 50 students. Everybody's gonna get a tiny little amount of pizza. Well, as we see an increased concentration of aerosols in the atmosphere, what we actually see is a decrease in droplet size. Every individual cloud droplet now has less water in it. Why? Because we have more droplets. The same amount of water spread over a larger number of droplets results in smaller droplets. Just like the same pizza split over a larger number of people means each person gets less pizza. Well, here's what that actually does. Tinier water droplets actually reflect sunlight a lot better than large droplets. Large droplets are more absorptive of sunlight. So tiny droplets actually make clouds brighter, and that reflects out more sunlight. That's the first indirect effect. So additional aerosols make clouds brighter. The other thing that happens, and so that has a cooling effect. The other thing that happens though, is because we now have tinier water droplets, those tinier water droplets usually can't form into raindrops. What that means is that they remain a part of the cloud. They don't grow big enough to become raindrops because the water is just too stout. As a result, the cloud actually becomes longer lived. And because there's now more moisture in the cloud because it's not raining out, that makes the cloud thicker. That too has a cooling effect. So for both of these indirect effects, the brightness of the cloud and thickness and the life of the cloud all result in additional cooling.